Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video on Math Basic Course. And as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on inside as we jump into the sections 5.1 to 5.3 quiz review in the Big Ideas Math Integrated Math 3 textbook. This is on some things regarding exponential functions, specifically the base e. And then we started some things on logarithms. We did their functions and just how you can evaluate them and some graphing for exponential and logarithmic functions. So you're going to see, I think, 25 questions in total among these three sections here. If you want to find this PDF down below, you can jump to the description section. You can find that, as well as graph papers. We're going to have to do some graphing, I'm sure, and the timestamps for each individual problem as well. Without further ado, I'm going to go ahead and get started. We're going to start with numbers 1 through 4, where they're asking you to tell whether the function represents exponential growth or exponential decay and explain your reasoning. So this would have been out of section 5.1, and its use would have really been out of section 5.3 when it comes to graphing. But the first one, f of x equals 4e to the negative x power. The matter of fact is that e is a number that's more than 1. It's around 2.7-ish. And since it's a number that's more than 1, you would expect growth. However, because this x in the exponent's negative, this is also the same as 4 over e to the x power, or 4 times 1 over e to the x power, whichever way you want to put it in your graphing form that you may be aware of. Once that thing was negative, if you consider an r value, once that r is less than 0, a negative number, you're going to be experiencing exponential decay. Every time x increases by 1, you are dividing another instance of e. You're multiplying another 1 over e, which is a number that's less than 1. That makes it become decay. And that's my explanation. If they say explain r is less than 0, r being negative 1 in that case, and you don't need to use the letter r, but that x is negative if you want to say that. Now you're going to see different numbers up here. And number 2, you have y equals 1/2 e to the 3x power. And again, this 1/2 has nothing to do with it. Maybe a starting value, but it's what happens as x increases. And because this r is 3, as x increases here, it's a positive number. It doesn't matter what kind. As long as it's a positive number, x increases. Therefore, you get to multiply more instances of e as we go on. Therefore, this is exponential growth. It's interesting. We have 4 questions out of the, I think, 25 on just exponential growth or decay. Is this a positive or negative number? Really seems to be the only question. And same with this one as well. Y equals e to the 0.6x. Look, the 0.6 is less than 1, but that doesn't change the fact that certain amounts of x will end up making this thing be e to the first and e squared as x increases, which means this is going to be exponential growth as well because r is greater than 0. Should probably box these. So exponential growth. Again, r to me is just what I'm referring to as 0.6 and all that. If we do any problems that have to do with continuously compounded interest, we use the letter r up there. So, number 4, f of x equals 5e to the negative 2x. Well, hey, it's a negative 2, and it's less than 0. There's an r value. It's exponential decay. Right? We're only looking at that. So long as that letter is just e, e representing the constant 2.7, that's what it's going to be. Now, if this number here was like 1/2, well, it's a different story. Anything that's negative would actually be growth. So it just depends on what you're talking about. We had a value more than 1 here. This value is less than 0, decay, greater than 0, positive is growth. All right, let's move to numbers 5 through 10, where we simplify the expression. This is out of both sections 5.1 and 5.2, because in 5.1 we referred to e, the exponentials, and in 5.2 was more logarithm. So number 5, we have e to the 8th times e to the 4th. They're treated just like you would x. You get to keep the base, add the exponents. Not just like x, like any number. 2 to the 8th times 2 to the 4th is also 2 to the 12th. The difference is 2 to the 12th, we might actually turn into its actual number of, I think, 4,096. E to the 12th, it's a number. It is, and it's more than 4,096, but it's also probably a decimal version. We're going to leave it just like that. So I think they're just reminding you that e is treated just like any other base. And if you want to evaluate it as a number, you absolutely can. So 15e cubed over 3e, 15 divided by 3 is 5, and e cubed divided by e to the first, remove the 1e down here and 1e from up here, you're left with 5e squared. Again, if you actually did e squared, which is around 7.4-ish, and then you multiplied by 5, okay, you get a number around, I guess, 37. Okay, but, you know, you could try it. Probably a little bit less than 37. But that's all they want as far as simplification, and I'm good with it. All right, 5e to the 4x cubed. Don't forget the fact it's 5 times e to the 4x cubed. Therefore, you get to cube the 5 and cube e to the 4x. Now, when you cube something that already has an exponent in it, you multiply those two exponents. 5 cubed is 125. E to the 4x cubed is e to the 12x. You get to multiply that 4 and that 3. E to the natural log of 9. This is the start of actually section 5.2. In section 5.2, we start to hit logs. Now, natural log, I might want to talk about this one for a second. And it kind of runs on a sentence when I do. E to the natural log of 9. Natural log is the same as log with base of e. Log base e of 9. Now, could I tell you what log base e of 9 is? No, I don't know e to what power gives me 9. I know it's a little more than 2 point something, but I couldn't say exactly what it is. That being said, we're doing e raised to that power. Logarithms are their goal of finding for you an exponent for this base and this result. So literally, when I said e to what power is 9, if it said log base 3 of 9, it would mean 3 to what power is 9. So log base 3 of 9 is 2. Log base e of 9, a little more than 2, because he's around 2.7. But that's just the exponent portion. I'm raising e to that power. I'm raising e to the number that I need to raise e to get 9. So I'm getting 9. So this is what cancels this thing out here. It gives you 9. Now, you don't need to turn natural log into log base e. This is something you're supposed to know. You're supposed to understand. But this is where that matchup is. Any b to the log base b of x is x, because you're raising b to the power. You need to raise b to the power 2 to get x. Literally. It says whatever the number is, I'm doing it, right? And that's the idea of that one. That's one of the logarithm properties to know. Number 9, log base 7 of 49 to the x power. Now, you might notice that I put parentheses around whatever I'm taking the log of, because log is a function. We're taking the log of 49 to the x power, given base of 7, and x is inside that logarithm as well. Now, wrapping parentheses around that, imagine the x wasn't there. Just log base 7 of 49. 7 to what power gives you 49 is the question. Well, that answers 2. However, let's just turn 49 into 7 squared to get a better idea of where the x goes with this. This is 7 squared to the x power. Now, we just saw what happens when you have power with power. In a problem, you multiply the exponents. So why do I bring that up? Because now this can be rewritten as log base 7 of 7 to the 2x power. This better works out a question. What power do I raise 7 to get 7 to the 2x? 7 to what power is 7 to the 2x? 2x. So this is once again another work of those properties. If you can match base with the value inside of there. 7 to the first power is 7. Well, 7 to the 2x power is 7 to the 2x power. It's exactly that. So that answers 2x. Those cancel each other out, if you will. The exponent grounds itself. There are kind of other ways. We're going to talk about that when we do more on properties of log. And I think that's section 5.4. When we do more properties of log. So you're going to see more of that process take hold. But it's because of what we're seeing right here that it actually happens. Now, number 10 is really no different than number 9 when it comes to what we're talking about and process. It's really, in fact, quite the same. Log base 3 of 81 to the negative 2x power. Once again, if I can turn 81 into 3 to a power, that can definitely help me, at least given this time of which properties you do know. And 81 is 3 to the 4th power. So I can turn this into 3 to the 4th, still raise it to the negative 2x that you see right there. Negative 2x times 4 is negative 8x. So this becomes log base 3 of 3 to the negative 8x power. Now, I'm trying to ask myself, what power can I raise 3 to get 3 to the negative x power? I keep going over here as if I had something else here, because normally what we do is we say, hey, equals some variable. 3 to what power gives me? And so if you ever see me move my mouse over there, I'm just used to that action and whenever I'm saying it out loud. This comes from years of teaching. Normally we do it for these problems, and we will probably do it in the next 11 through 14. But here, 3 to what power is 3 to the negative 8x? Well, negative 8x. Once I match that base with that value inside as the base, then just the result is the exponent. And that's what logs are. They give you exponents as results. A logarithm is the inverse of exponentials. Okay, let's move on to numbers 11 through 14, where we rewrite in exponential form or logarithmic form, one or the other. This would have made a little more sense to have these ones take place probably before numbers 8, 9, and 10, specifically 9 and 10. But here we have log base 4 of 1,000. 1,024 equals 5. I mean, this is a true statement. They're not asking you to solve anything. They're asking you to rewrite this in exponential form as its logarithmic form. The form is, this is log base 4 of 1024 equals 5. I already told you the results of logarithms and exponent. I literally said base here. That might help you say 4 to the 5th equals 1024. And there's really only one way to write this around that makes it a true statement, of course, in exponential form. 5 to the 4th isn't 1024. 4 to 1024th isn't 5. So, make sure it makes a true statement. And in some cases, learn something about the statement that's being had. Whether you're just learning for the first time what 4 to the 5th is, whether you're learning right here for the first time how you use exponents as bases and negative numbers as fractions. I hope we've learned it before, but it just so happens to be that 1/3 to the negative third power equals 27. And that's the answer. If you want to double check on that, negative exponents flip fractions around so it becomes 3/1 cubed. And 3/1 cubed, of course, is 3 cubed. 3 cubed does equal 27. That all pans out. It seems to work. So that's the answer. You do have to wrap 1/3 around parentheses so that the negative 3 applies to both portions of the fraction. Whether this was 1/3, 2/3, whatever, it needs to go down to the 3. So if there's one thing that is required in that answer, it is the parentheses around the fraction. On number 13, we have 7 to the 4th equals 2,401. I suppose that's a true statement. Let's go with it, right? But we need logarithmic form out from it. What do we say about the base right here? Log base 7 is your base here. So this is log base 7 of, now if you forget what's right here, just remember the result of of a logarithmic function is the exponent, so 4. So this is where 2,401 goes in. 7 to the 4th equals 2,401. That's what I was pointing at before. This to the that is that. There's your log form for this one. And then lastly, number 14, 4 to the negative second power equals 0.0625. I'm sure that's true. After all, 4 to the negative second is 1/4 to the second, which is 1/16. 1/16 must be this number. If you took me a second, I'm sure I could also confirm that for you. Anyway, let's do log base 4 of 0.0625, and that happens to equal -2. Yes, negative exponents leads to division of this number a certain number of times. Will often lead to numbers less than 1 in this case. So there's logarithmic form. Now, none of these things we can officially yet confirm with the calculator until we learn more about logarithmic properties. We're going to do it, like I said, in section 5.4. Right now, our only 2 log buttons that we have are the common log, which is log base 10. It'll just say log on there. And natural log, which is log base e. And these are going to show up on at least numbers 15 and 16. They said evaluate the logarithm. If necessary, use a calculator and round your answer to 3 decimal places. So this is also out of section 5.2. They're asking for a log of 45. Notice that the base is not shown. That it is implied, though, that it is the common logarithm of log base 10. Now, whether or not you care about that part is actually irrelevant because we get to use our calculator for this. But this is asking you 10 to what power is 45, and we're about to get that answer. So, in your calculator, if I hit log right here and 45, it's actually going to tell you 10 to what power is 45. I just know it's a number between 1 and 2 because 10 to the first is 10 and 10 squared is 100. So 1 point something, 1.5, 1.65, whatever. They said to, how many? They said to 3 decimal places. So I'm going to say 1.653. 1.653. There you go. So there's the 3 decimal places that we have to do with the calculator for that particular problem. That's one that we can use in the calculator to our current level of knowledge on logs. Same with number 16. Natural log of 1.4. Now that's the same thing, just so you're aware, as log base e of 1.4. E is a number. E is around 2.7. 1.4 is less than 2.7. There are 2 kinds of numbers that you can get that are less than your number. One is a number that's strictly less than 2.7 but more than 1, which means you're taking some sort of root of your thing. So therefore, I expect a fraction answer. I expect just like a decimal, 0 point something. Another version of it is when you can get a number that's less than 1, between 1 and 0. You can't take logs of numbers that are 0 or negative, but you can take log of a number between 0 and 1. And that's when you're dividing 1 by your e a certain number of times, and that's when you're going to get a negative answer. This, I don't expect a negative answer here, but I expect a 0 point something answer here. Now, for log base e, of course, we use natural log. We have the ln button. It's right here. So I hit ln of 1.4. Didn't even need log base e, but just reminding you what it is. So there's my number, 0.336. 0.336 is the rounded value. Now, to confirm both of these, if you like to, once again, to show you that it is log base e and log base 10, let's go back to the calculator. Let's use our rounded values for it, if that's all right. Let's do 10 raised to the 1.653 power. Because I under-rounded, then I'm going to get a number slightly under 45, but that's the idea. 10 to this power should be about 45, right? And it is. Now, e, second, and hit natural log e to the 0.336. Again, it's under-rounded, so it'll be close to 1.4 underneath. Close to 1.4, but you can see that that's what it was intended to be, and that's what we found in these calculations. Let's go to number 17, and in its current form again, and they're expecting it this way. This is how they want it. You don't know how to do this in the calculator just yet, or at least my calculator doesn't have the functionality of changing bases as a feature. There is a way to calculate it like this. Again, I'm not going to state it yet. But we are trying to figure out what log base 2 of 32 is, and we can actually do this without a calculator. So, as you've probably heard from the previous questions, then I'm going to set it equal to x, so we can rewrite it in exponential form. 2 to what power is 32 is the question that we're asking. So if you rewrite it in exponential form, that'll probably give you your best understanding of what we're doing. And that would be 2 to the 5th power. If you have the same base here, you match your exponents. X equals 5 is the answer. So what is log base 2 of 32? It's 5. I'll just write it one more time in this form so we're not looking at some x like we were solving a variable. We were evaluating this right here. Log base 2 of 32 is 5. Okay? So hopefully that helps make sense of what we wrote before on this set and even this set right here, how we came up with them. There it is. Number 18. We'll come back. Number 18, 19, 20. We're going to graph the function and its inverse. Now that we've gotten into, and actually it says section 5 too. Let's see what kinds of graphs we do later. You know, we don't do graphs later. I'm going to treat this more like 5.3, as in we already learned the section. That's where you're doing quiz review. I'm going to graph them individually as if you learned them the way that I taught you how to do the graphs for them. So f of x equals log, I'm looking at number 21. 1/9 to the x power. We are going to use, because it's an inverse as well, we're going to use the bigger graph, not the bigger graph, the squared off graph paper like this. 1/9 to the x power is kind of an interesting number set. It's very tall or very decay-y. This is 1 times 1/9 to the x power, as if to say that there's no vertical shift. So our horizontal asymptote is on the x-axis, y equals 0. When x is 0, this becomes 1, and 1 times 1 is 1. So the a value, we go a units up above the asymptote for this. And you multiply by 1/9 every time x increases by 1. So this goes down to 1/9 right here. Very, very small. Very, very small. And you divide by 1/9 as you go to the left, which is the same as multiplying by 9. Very, very tall. Very, very tall. If x was -2, I'd go up to 81, which I can't reach. If x was +2, I'd go down to 1 over 81, which is really too small to plot as a point. Sometimes I say point as a plot, so I'm glad that I actually said it correctly that time. And this blue graph here represents the original function f of x equals 1 times 1/9 to the x power. Now they said graph its inverse. Now let's take its inverse, figure out what it is, and graph it that way as a result, and we can see if it looks to be the inverse that we hoped for. So in order to do this, let's turn this into y and swap x and y. That's our inverse step. This is a little bit of 5.2 going into play by taking the inverse, or even section 4.6. if you think back enough, but we learned logarithms at this time. How do I ground y? You can rewrite this in log form. Y is the exponent, the result of an answer to log base this of that. Log with base of 1/9, base 1/9 of x. So this is the inverse function. This is inverse of f, and this is log base 1/9 of x. So we're going to now graph this one. How do we graph a log function? For me, it always starts with the domain. The domain is that you can't take logs of negatives. The thing inside of the log must be greater than 0, and so that's your domain. If that's your domain, that means 0 is that barrier for which we cannot cross. It makes it your vertical asymptote. This is part of the confirmation that so far what we're doing for the inverse is correct. This has a horizontal asymptote, y equals 0. This has a vertical asymptote, x equals 0. Inverses are all about swapping x and y, and that's actually what they would want you to do with this graph, is graph the original function and just swap the x and y's. But let's start doing some more on it. What I would do after that is I would take the log of 1, because anything to the 0 power is always 1. That means the log of 1 of any base is always 0. That means 1 away from the asymptote, I can plot right here, boom, 1, 0, given that there are no vertical shifts, which there aren't. So there's an actual point on the graph, which seems to match with 0, 1 right here. Swap that, you get 1 comma 0. So far, so good. We did say that y is the result, this thing here, is the exponent that we get for this. 1/9 to what power gives you whatever x value you're talking about. So let's plug in x values that would increase or decrease our exponents by 1. What would increase my exponent by 1? Having another power of 1/9 multiplied into our set. 1 times 1/9 is 1/9. And if I do log base 1/9 of 1/9, I get 1. Therefore, if I go up 1, I can multiply 1 by 1/9, and I get, boom, that little guy right there. It's not on the y-axis right there. Sorry, this is so zoomed in. But that's 1/9 comma 1. If I go down 1, then I'm dividing by 1/9, which is multiplying by 9. What gives me exponent of negative 1? Dividing once by 1/9. So going down 1 times 9. That's divided by 1/9. So it goes out here to 9, negative 1. And I have a point negative 1/9. So everything looks like, and that's all I can fit, everything looks to be the inverse of that other graph right there. And I only plotted points that would really get me some good numbers out from it. 1/9 ain't great, but it is one of the best points that I can get on the decay side of it. So there's the true reflection across y equals x. It seems to confirm that, yeah, it reflects across this line right here if you really look dearly at it. So we did find its inverse using methods in 5.2 and from before. Whoopsie, I wanted you to see that for a second longer. In 5.2 and everything you saw before. All right, let's go to number 19. Well, they had to throw a natural log in. I'll tell you what, we never graphed natural logs in section 5.3, but then again, this is a 5.2 thing, but natural log, again, is just log base e. So let's learn it. Let's learn it right now together. Now, what do they expect you to do? Take its inverse, graph the e graph, and then reflect it over. We'll still graph the e graph. Let's just start with this. Let's start with the domain. The domain here is, again, you can't take log of negative numbers, natural log or otherwise. X minus 7 must be greater than 0. If you add 7 to both sides, x must be greater than 7. This is the inkling of how this graph works. X is greater than 7 means we have a vertical asymptote at x equals 7. Now, I wish it were a different number because we really can't plot many points in this direction. It also means we also can't plot many points on its inverse function, unfortunately. So we'll just say what we can on this. Once again, the log of 1 is 0. Now, what value of 8 would give you 1 inside of here? 8. 8 minus 7. 8 is 1 away from 7, so it just makes sense that when we go 1 away from here is where we turn into 0. There's no vertical shift. There's no plus 3 or anything like that, so it's just right there. And y increases by 1, the exponent, every time you have another power of e multiplied by your set. Remember, this is log base e. So when I increase y by 1, I multiply 1 by e, and I get my next value out. E is around 2.7, so I'm going to go ahead and go 2.7 away. 1, 2.7 from the asymptote. I can't fit any more points other than that one that way. The next one would be e squared. When I go up to 2, e squared is around 7.4. I can't fit it. I can divide by e. 1 divided by 2.7-ish is, it's around 0.36, I think I remember it is. Around 0.36, and I can do that and get another little minute point, divide by e again. So very little that I can plot on this given my graph size and scale. Could I change scale? Sure. Will I? No, I don't think I will. So there's that graph. Let's take its inverse now. Y is already here, so let's swap x and y. We get x equals natural log of y minus 7, and your goal is now to solve for y. Log is by itself right here. Remember, it is base e, so we are going to ask e to what power gives us y minus 7, or really e to the x power. We're not literally solving for it, but e to the x power gives you y minus 7 is the exponential form of this thing, right? It's not just a magical e that appeared. Remember, this is log base e, like that. So we can add 7 to both sides, and you'll get y equals e to the x plus 7, or in inverse form, inverse of f equals e to the x plus 7, like that. So this is what we're going to be graphing here. That is the inverse. We'll graph its inverse, and this inverse has 7 as its vertical shift. That means its horizontal asymptote will be at y equals 7 way up here, and we're going to graph above it. So like I said, just as little room on this one as we had on the other one, but it seems to match. This is x equals 7. Its inverse has y equals 7. And again, they're fine with you graphing by flip-flopping x's and y's. I'm just graphing these with you together and confirming that they reflect. So I'm going kind of the other way, kind of in a 5-3 way. E to the 0 is 1. It's still no change as far as this goes. Whatever a value is written in front of here is how far you go up given no horizontal translations, just like here, given no vertical translations, we get to go 1 away from like that. And now we get to multiply by e every time x increases by 1. That's literally how exponents work. X goes over by 1, e times higher than that, given that we already have our shift of plus 7, and we do. And that's all I can fit going up. If I go down here, I divide by e, again around 0.36, and then around, I don't know, 0.1 something something, and it just goes like that. So here's our graph on this one by not changing scale. And hey, it sure looks a heck of a lot like the inverse of this other guy. When you reflect across that y equals x, anything that was a point is now reflected across. Let's call some of them out. On this first one here, this is 0, 8, and this is 8, 0. There's a flip-flop. Let's do this next one. This is 1, 7 plus e, and this is 7 plus e, 1. Around 9.4. Ooh, 1, 9.4 and 9.4, 1. So there's the reflection. It all seems to work out. Number 20. Another logarithm. Maybe a little easier to plot, but we're only going to get so many points on this one as well. Actually, less so. This is f of x. So this is going to sound a little bit like a rehash of the last one, only instead of multiplying by e, we multiply by 5. Log base 5 of x plus 1. Let's start with this graph. So on this one, we go back to our domain talk. X plus 1 has to be greater than 0. X plus 1 has to be greater than 0. Subtract 1 from both sides, x is greater than negative 1. X equals negative 1 is our vertical asymptote of this logarithmic function. Like so. The log of 1 is 0, so this goes right here. When you plug in 0 for x, you get 1, and log base 5 of 1 is 0. So there's that point, and then we multiply by 5 each time y increases by 1. Up 1 times 5 over from the asymptote, not your other point. Up another 1, another 5 times over, which is 25 over, can't fit it. Down 1, we divide by 5 this direction like that, and that's really all I can fit. At least the numbers are a little bit cleaner sounding, even though 1/5 is still, no matter what you do, you're going to have a fraction kind of go in that direction, even if you're dividing by 2. So there's that guy. Remember, it is increasing. It's going to go up to y equals 2 when x equals apparently 24, because that's 1 away from 25 as we're shifted 1 to the left. So there's your logarithmic graph. Let's take its inverse and see that inverse one graphed on here. Swap x and y. Whoa. Wow, wow, wow. And solve for y. We are in logarithmic form with the log by itself. 5 to the x power equals y plus 1 is our setup. Subtract 1 from both sides. We'll get its inverse. Y equals, as the inverse, 5 to the x power minus 1. So here's the inverse function as an exponential. The negative 1 is a vertical translation. We go 1 unit down as the horizontal asymptote, and everything else follows suit. Once again, there's an a value here, an a value of 1. So when x is 0, y is going to be 1 up from there. Boom. Same place as before. 0, 0. Swap x and y is still 0, 0. And every time x increases by 1, you multiply by 5. So 1 times 5 is 5, which is at 1, 4 instead of 4, 1. Hey, that makes sense. If I want another one over, I'd go up 25, and I can't fit it. Divide by 5 as I go to the left. All this should sound very familiar to what we just did for the other function. It's just inversed. It's not changing signs, it's changing variables. X and y changed. And once again, sure looks like an inverse there, and we're graphing both of them. We're having fun. We're making sense of things. I hope y'all are without your questions there. Again, if we were in 5.2, we'd probably take the inverse, graph the exponential first, and then do the swap. Because now that we've done 5.3 and some graphing there, and it doesn't look like we get to do graphs for ourselves, then we'll do that. Now, we're going to take a look at section 5.3 here, but they're just asking you to write a rule based on the graph. So you don't get to do your own graph, but I also get to explain away how these graphs are based off this. So f of x equals log base 3 of x. Let me copy and paste this graph into here. It might be a little blurry. A lot blurry. Now, what we're going to do is come up with a g of x equation. Here's how f of x equals log base 3 of x would have looked. Vertical asymptote on the x-axis. 1 away from here is 0. By the way, these are scaled by 2, so you would have gone here. And then up 1, you get to go times 3. Up 1, another times 3 like that. And down 1 divided by 3. So your graph would have looked like this. Now instead, what happened? There's a little bit of a translation at least. We take this graph that we have here, and we seem to have moved it at least over 1 to the right. It looks like we even went up at least 1 right here. Well, actually over 2 to the right because it's scaled by 2s, and 1 right there. So boom, there's a clean match, right? Now, how did I know those things? Well, this is why I wanted to plot this one right here. First of all, 1 to the right we know because the asymptote moved. Before it was on the x-axis. That's the default. X is greater than 0, right? Now, apparently, it's x is greater than 2. So there's 2 to the right. How do I know it's 2 what? Because my reference point, I know log of 1 is 0 like this, so I know that I need this point to still match here. So I matched that one first before I spoke on anything else, such as stretches, reflections, anything like that. It's not just a stretch if we do need to do that translation on there. So this does seem to be a match. So what are we saying? We are translating 2 right and 1 up. So it says write a rule for G given this transformation. Boom. It seems like a slogan for something. G of x, 2 right, 1 up. So G of x takes your f of x, where we're going 2 to the right, would look like that, and 1 up where we look like that. So it's still log base 3. There's no change there. They're not going to change that part. It's log base 3 of x minus 2, and then plus 1, like so. This does give you the domain x is greater than 2, because x minus 2 has to be greater than 0. So that seems to pan out. The plus 1 is that upward shift. You take the log of 1, you get 0. Plus 1 is the shift upward. So, although we don't get to graph, we do get to talk about the appearance of graphs with them. Number 22. Number 22, we have f of x equals 3 to the x power. And I hope this wasn't too blurry for us because I'm about to do it again, copy paste. This is an exponential function, and we're asking what's happening with that 3. Now, there's more than one answer for any of these you could technically do. But given this, we want to get the easiest answer out of this for ourselves. So this 3 to the x right here, if we originally graphed it, it would have had a asymptote at y equals 0, and 3 to the 0 power would have been 1, and we would have gone times 3 to get some other points divided by 3 here. This is our 3 to the x graph. So what's happening from here to there? Clearly a vertical translation. If you see the asymptote, it goes downward. So let's bring it on downward and see if there are any other changes. Not really. Looks like that's it. It's just a translation downward. The 1 still exists here unless you were talking about changing A and H, which I have no intention of doing that. Looks like we just translate 4 down. 4 down. It's more than 3 down. It's 4 down. Right? It's just a translation there. So our G of x equation just takes whatever we had for f of x and it's subtracting 4 from it to affect the y's there. So G of x is 3 to the x power minus 4. That is our equation for number 22. And the last one of this set, number 23, this one's actually going to be a little bit tricky to talk about here. Unless you saw what we talked about in 5.3, I sure hope that you have something involved. F of x equals log base 1/2 of x. I guess it's been helping, hopefully, that I've been doing the original graph first, and this time I think it's going to even more so matter. So let's copy paste this graph guy right here. All right. At least these are scaled by 1s. That helps ease things a little bit. Now, log base 1/2 of x has a vertical asymptote at x equals 0. Hey, this graph has the same thing. So it looks like there's no horizontal translation change. Let's see if there's a vertical translation. Log base 1/2 of 1 is 0 like anything else. So log of 1 is 0. Okay, that point hasn't changed either. It doesn't really look like a vertical translation. But what is changing? Every time the exponent increases by 1, we're multiplying by another 1/2. That means this goes this direction instead of the other direction. Half of 1 and half of a half is a quarter, and then an eighth and stuff like that. It shrinks. And then we divide by 1/2 as we go down by 1. 1/2 to the negative first is 2. And then, 4, etc. And we would keep doubling. So it looks like it goes this way. So what is changing here? Well, you could say, hey, we changed the base of 1/2 to a 2. No, it's supposed to be the same. How do you say it? It's supposed to be the same base. It's supposed to be the same base. What we're doing is something else here. As we know from other transformation days, this thing's flipped over. This thing's flipped over. It's reflected over the x-axis here. If you notice that this point here goes from -1 to +1, and from -2 to +2, and likely down here, -3 to what hits +3. This one looks like it's changing as well. So that's what's happening here, right? It is flipping itself over. That's making the y's opposite of what they would have been. This is a reflection over the x-axis. Reflect I always write rect first. Reflect over x-axis. So as an equation, our g of x equation is just the opposite of our f of x. So it's going to be negative. Negative, and just -1. It didn't stretch or anything like that. So we're not hitting every kind of graph under the sun. You definitely want to look at more graphs that we did from section 5.3. I have other videos. I have other videos of old that if you go to Mr. Robinson, whatever, log graphs, you're going to find a lot where I do the same explanation like this. All right, we got 2 more problems. Number 24. A local bank advertises 2 certificate of deposit, CD accounts that you can use to save money and earn interest. The interest is compounded continuously for both accounts. This is where we where we're going to use the formula. A equals PE to the RT. P is your principal interest. E is that number 2.7-ish to represent continuously compounded interest. R is your interest rate in decimal form. T is the amount of time in years. And A is the accrued amount in dollars. You deposit the minimum required amounts in each CD account. We have the following. Minimum, you probably can't read this. Let me copy paste this. It'll be blurry still. Let me get the higher quality version of this. This one you'll definitely be able to read. I'll have to zoom it out, even shrink it to size. Okay, can you see that? Did you see that? We have these numbers here. So, as advertised, CD specials, not compact disc, certificate of deposit. So minimum for each of these. So let's talk about that. How much money is in each account at the end of its term? How much interest does each account earn? Justify your answers. So in the first one, we'll call this one A, and second one, we'll call this one B. 36-month certificate of deposit, $1,500 minimum balance. If we apply the minimum there, actually, let's call them 1 and 2, because I want to say A sub 1 and A sub 2 here. So for these things here, my principal interest, P sub 1, is going to be $1,500. The interest rate is 2%, that's 0.02, and something that they never spoke of in the section itself, because they didn't get to do a lot of these problems. I'm glad we're doing this one here, because we didn't get to do a lot. The time is 36 months, but you do not do time in months. You do it in years. So 36 months over 3 is 12 over 3. 36 months over 12 is 3 years. So T is 3. It's not 36. The book never did address that. Maybe it did in the formulas, but it never did problems with it. So A sub 1, how much money is accrued over this time if you do this here? You have $1,500. This is times E raised to the 0.02 times 3 power, or 1,500 E. I always like to simplify these when I can. 0.06 power. Now I'm going to go to my calculator. We should get growth. We talked about how if that number's positive with E, it will represent growth as long as it's not negative. So 1,500 E to the 0.06 power is 1,592.75. That's money. It's about, this is rounded, $1,592.75. How much interest does each account earn? I wonder if they're saying the overall, because the original is 1,500, the difference is $92.75. So when it says how much interest, I believe the interest would then be $92.75. I don't know if they're being specific about find the difference between your numbers. I'll just go ahead and say that. So if we do 1,592.75 minus 1,500, that's $92.75 interest earned. Okay, that's for the first one. That's A sub 1. A sub 2 has all the information down in 2, so we can spell that out. I'm just going to, Anytown Community Bank, what was the first one? CD specials. Anytown Community Bank is P sub 2. Principal is $2,000 instead of $1,500. Interest rate of this is 3%, so everything's already looking bigger for that. We're going to get more money on this, clearly, as we started with more, higher interest rate, and more time. Time is 60 months. 60 months divided by 12 is 5 years. So when we work this one out, it's going to be A sub 2 equals 2,000 times E raised to the 0.03 times 5 power, or simplified, 2,000 times E to the 0.15 power. So significantly, it's not just more money there's going to be overall, but it's a greater difference from the last one that we had because higher everything. And this is going to be $2,323, about 2,323 and 67 cents. That's in monies. That's in dollars. And so that interest rate there, the interest earned on this guy, is about $323.67 interest earned. Excuse me. I should probably box those ones. I think that was the official question that they had on both those parts. Okay. So, describe the benefits and drawbacks of each account. Okay. I guess the thing is you need to do, whoops, not number 24, part B. Oh, this was part A. Hold on a second now. So part A is here. So when we look at these things, what do they say? They said, these are things you can save money, but you deposit the minimum required in each thing, and here are the terms. So although you get more money from this one here, it's more of a difference, significantly more. You need to invest more money, and you need to keep it in longer. So although the second account, what do they call it? Anytown Community Bank, I'll just call it ACB. Although ACB, Anytown Community Bank, actually I'll type it because you might be having me on mute. Although Anytown Community Bank has yields a higher difference, a higher interest rate, you must invest a larger minimum and keep it in longer, and keep it for a longer term. So there's benefit if you can wait another 3 years. No, 2 years. This was 3, right? Another 2 years, but you still also have to commit more money to it. So that's just kind of that's everything as one. That's the benefits and drawbacks in one compared to the other to me. All right, last question, number 25. The Richter scale is used for earthquakes. It's used for measuring the magnitude of an earthquake. The Richter magnitude R is given by R equals 0.67 times the natural log of E. E is not that E base that we're talking about. This is a capital E is a variable. Plus 1.17, where E is the energy in kilowatt hours released by the earthquake. Graph the model. What is the Richter magnitude for an earthquake that releases 23,000 kilowatt hours of energy? This is one where you're going to go more to the graphing calculator, and let's fit something within a window range. So we're going to turn R into Y and E into X for this. Let's go into Y equals 0.67 times the natural log of X. Just remember that's our E, our energy, I believe it was, plus 1.17. Now, this is something where eventually we have to do 23,000. So we're definitely going to change this window range here. Let's go from X is 0. We don't care about 0 energy. Up to, let's just say 25,000. Let's just increase, up to 25,000 so we get a little more headroom. Now, I don't know what we're going to need for Y here. There may be some, I don't know if negative magnitude's a thing, but let's just go up to 1,000 and see what's going on. Logarithmic graphs tend to go over that way pretty hard. This is actually, wait, hold on. This is magnitude, right? We don't do 1,000 magnitude. Probably don't even do 0 magnitude. Let's go from 0 to 15. I think that should suffice. There we go. That's enough. 1,000. I forgot what we were talking about here. All right, so there's enough of that curve. So that's our graph to me. Now I'll show you the window range that I type out when I bring this into here. So for this, graph it. You betcha. There's our graph. This went from 0 to 25,000, and this is 0 to 15. I probably should have gone lower. Magnitude of 15 means the end of times to me. All right, so given that, we're going to estimate around 20,000 right here, which to me is going to look like 1, 2, 3, 4, 5, 6, 7, probably around 7 to 8-ish. We're going to substitute it, obviously, within here. It says, graph the model. What is the Richter magnitude for an earthquake that releases? Oh, 23,000. Oh, 23,000. I thought they wanted 20,000. So good thing I went to 25,000. It's going to be probably closer to 8, I'd say. But we're going to go ahead and do that in our calculator. Now, we have some options here. We have learned in this set that we can go to variables, vars, y-vars, and function, and hit y1. Here's our equation. And in parentheses, if we type our input, 23 thou like that, we'll get our output. So our output's going to be 7.89 or 7.90 when rounded. So R of 23,000 kilowatt hours is about a 7.9 magnitude. So like I said, around 8. And whoop, there it is. Okay, guys, that's it. That is the quiz review. So I did mention some things that this kind of felt like it did out of order in some ways, how they front-loaded some things, here and there. They didn't do a lot on graphs, but then I saved you with it with a lot of graphs on there. They did quite a bit, though, even still. It's a pretty good quiz review, all told. That ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. Good luck on whatever it is you do with this information. And take care. I'll see you in the next one, which apparently should be 5.4.